So for this video, we're going to see how we can compute z-scores corresponding to areas using the inverse normal function of the calculator. We'll also see how to do this with percentiles and other different arrangements. It's all essentially the same thing, just with different language. Now for this first problem, we want to find the z-score that corresponds to a cumulative area of 0.3632. And to do this, we go into our distributions, so second vars, and scroll down to our third option here, inverse normal. This is the function for specifically finding values given areas to the left. And that's important that this function only works for areas to the left. But anyway, we get this. And here we have our values where we get the area, in this case to the left, is 0.3632. And we want a z-score, importantly here, where because we want a z-score, that means we want the mean mu to be 0 and the standard deviation sigma to be 1. Paste that. If you don't have that menu popping up, you do inverse normal 3632, comma 0, comma 1. Run that number, and we get our z-score approximately. So this is part of why I would recommend working with the calculator instead, because you don't have to deal with sifting and averaging and getting something close when there's so many different options. It's just a massive headache. This is far more efficient and effective for this kind of problem. Next, we're going to look at how we can compute a z-score given an area, but instead we have an area to the right. Now, with these, we have to be careful of the fact that our inverse normal function is designed for only areas to the left. We're always designed in terms of that traditional accumulation up to a value. So if you want to find things beyond, if this area down here is about 7%, we need to get its complement first. So we take 1 minus 0.0668, and we get that to the left of it. This whole region out here is going to be about 93% of data. And so it's very important here that you understand how this type of thing looks like in terms of a less than, in terms of a greater than, in terms of the type of region that we're looking for, because that's what determines whether or not we can use the calculator, or at the very least how to put it into the calculator. But from here, we have what we need, so we hit second vars for distributions, inverse normal, and we put in our area in this case, which as we saw was 0.9332. And then we run it, where if you don't have this input, you don't have this set up, you use the commas, but you should get a z-score of about 1.5, up to rounding, where it's important to note here that we can get some significant differences with rounding depending on exactly what we need and exactly what we're asking for. Usually with z-scores, we round to 2 decimal places for a matter of consistency and for what fits the table, but there's no guarantee that that's exactly what we'll be dealing with. Next, we're going to look at how we can get z-scores given percentiles, and this is actually the exact same as the area stuff. So P5, that means we have 5% to the left. That means we have an area of 0.05. So that's just a classic inverse normal. 0.05, 0.1 since we want a z-score. And we get our value up to rounding of about negative 1.645, which is wonderful that I'm contradicting myself right in here. But again, this is because they're using the table making those guesses. Don't use the table unless you have to. For the next one, if we want 50, it's functionally the same thing. And I'll actually just pull up the output here and show you how you can just make that adjustment quickly. Just delete this value. And now we have an area to the left of 50, comma 0, comma 1, because we want a z-score. Run it, and we get 0. And that should make sense, because you have 50% to the left of the mean, and the mean for a standard normal distribution is always 0. So you shouldn't need a calculator for that one, but it's good to confirm. Like, you might be in a rush and not realize that you're doing something that's more obvious than it looks. For our last one, we want to find the 90th percentile. It's the same thing, although it's not quite as nice. But hopefully with, the empirical rule in mind, you should have maybe a rough estimate for where this should end up. But here you put in the 0.9, and you run it to get about 1.28. That 1.28 is an important one. we're going to be seeing it a lot in Chapter 6, and then we're going to be seeing it again in Chapter 7. We might even see bits of it again in Chapters 8 and 9, that you have 90% to the left of a z-score of 1.28 or to the right of a z-score of negative 1.28. That's actually really important because it's a value you see pretty regularly, but we'll see why that's important later. For our last bit here, we're going to look, instead of talking about z-scores, how these things work for general distributions, where here we're talking about police officer safety standards, where they have a mean of 50 and a standard deviation of 10. So this is a approximately normal distribution, because it's testing. Usually we build tests to be normal. And we want to find the cutoff for the top 10. Now, if we want to do this with a table, that would mean we want to find z-scores corresponding to specific values, and you got to do some conversions and do that nasty work with the table where you got to find the one that's closest to 10%, and you don't want to have to deal with that. What you really want to do here is understand that the inverse normal function actually works just as well for this. It's just not what it's defaulting to. If you want to work it with that, what you would do is get into inverse normal, and in here, because you have top 10%, that means you want 90% to the left. And 90% to the left, like I said, 1.28 is a pretty common value. It's one to know, but we're going to pretend we don't know that. We have 0.9, and even if we do know that, we don't know how it fits for a perfect distribution as it is perfect. Normal, non-standard. It's not perfect by any means, but we have that mean of 50, and the standard deviation here is not 1, the standard deviation is 10. So instead of doing this work here with the estimation and the z-score and then the conversion, we make the calculator do all the work for us, and then we get our answer, just like we would expect. So just to be sure, let's get one more problem in the flavor of finding specific values given normal distributions. So here we have that you got women with a mean cholesterol of 1.79 milligrams per deciliter, so a really specific number, and a standard deviation of 38.9. And we want to find the highest total cholesterol for a woman that can still be in the bottom 1%. So thinking in terms of our distribution, it means we're looking for the cutoff for that bottom 1 there, the first percentile, as it were. But we can do this table-wise, or we can just recognize our numbers. Inverse normal, 0.01, 179, 38.9, and truth be told, numbers as they are, it's just that easy. Where it is very important here to note, though, that comparing our number of about 88.505 to this 88.363, they're close, but that is something of a noticeable distance, and in terms of your value on a homework assignment, it might complain that you're incorrect, even though I would say you're actually more correct than the book is. It's a point of real contention that's only going to get worse in 5.4. All I can say to that is I'm sorry. I don't know why the book insists on being old-fashioned and kind of stupid about this, but it's what we're working with. Anyway, we'll also see how to do this stuff in Excel, at least some of it, as well as how to handle stuff in 5.4 in the calculator next.